In a recent interview, I casually mentioned that there had been a revolution in the ability for astronomers to determine the ages of stars using a technique called astroseismology. And after we briefly talked about that and moved on, a bunch of viewers wanted a lot more information and wanted an interview with somebody who specializes in astroseismology. Well, your wish is my command. And so I looked for somebody who specializes in astroseismology and had been publishing some work in this field. And I think I got the perfect guest. So my guest today is Dr. Marc Hon. He is a postdoctoral scholar, works with the TESS group and MIT, and he specializes in astroseismology. Specifically, he used this incredible new instrument on the Keck Observatory called the Planet Finder to measure the slight oscillations on a nearby K-dwarf. This is a star that is smaller, less massive than the sun, and presumably going to be a lot longer lived. And they're really interesting, especially for the search for their habitability, for life on planets orbiting around these stars. And so he was able to measure the wiggles and jiggles on the surface of the star with incredible precision. And there's a lot of really interesting implications for astronomy, being able to determine our place in the universe, the age of the sun, the composition compared to the ages of other stars. When are some of those big red giants going to explode as supernova? This is the field of astroseismology. Enjoy this interview. Marc, I've got a very advanced audience. They know a lot of stuff, but we're going to spend our entire episode talking about astroseismology today. So let's sort of make sure that everyone's on a common playing field here. What is astroseismology?
Astroseismology is the study of stellar pulsations to learn about the interior and the dynamics of stars itself. So you can measure pulsations in stars through a few different ways, some of which the most popular right now are the variations in the intensity of light that we see from the star, as well as there's another approach which uses radial velocities. You're actually measuring the contraction and the expansion of the star over time.
Right. Okay. And when was this pioneered? When did we first realize that you can measure these pulsations in stars and use that to get at useful information about the star?
Well, similar to a lot of what we've learned about space and other stars, it all began with the sun. We first started to measure the velocity at the surface of the sun many decades ago. And that's when we realized that the sun was actually showing these rather periodic variations at the 5-minute time scale. It's what we know now as the solar oscillation spectrum. And from there, the whole idea of helioseismology began, and we started to learn a lot about the interior of our sun. And it's only over the past decade or so that we've really been extending this knowledge of ours to other stars. And we found out that other stars also pulsate. Well, many other stars also pulsate in a similar way to our sun. Not all of them, because how stars pulsate is very dependent on, say, their mass or their composition, for instance. But there's a whole host of other stars that we call them solar-like oscillators that pulsate in a very similar fashion to our sun. And that's because they share a similar kind of stellar structure to some degree with our sun.
So let's imagine you could fly down to the sun with fireproof boots and you could stand on the surface of the sun, which you can't. It's a plasma. But if you could. Now, you mentioned that there are these sort of oscillations and pulsations. So what would you see around you in terms of like altitude as the sun was going through just its normal, regular pulsations?
Well, we like to characterize stellar pulsations in terms of spherical harmonics. These are the kind of mathematical tools that we use to describe the geometry or the patterns of these kinds of waves that propagate throughout the entirety of the star. And we know for the sun, for instance, that it doesn't pulsate in just a single, what we call a pulsation mode. So it doesn't pulsate in just one single geometry. It's actually a superposition of all these other kinds of waves, patterns of modes on top of one another. So if you were to be at the surface, you would actually see, if you could disentangle them, you'd see, just a superposition of all of these simultaneously. And it's not like you would actually see the star just slowly expanding and contracting inward and outward at one go. You'd see a lot of complicated activity, complicated motion that's going on at the surface.
I mean, would it be kind of like standing on the ocean in a place that's very chaotic? Like maybe there's, it's in a bay and there's a lot of reflecting waves that are coming back and forth, and so you've just got a lot of chop on the water. I'm sort of imagining though, like, would you see the surface of the sun contract from you by 100 kilometers over the course of an hour and then come back up, or would you just see much more minor variations and ripples?
You would see much more minor variations. Well, of course, what we expect to see, well, if you could see them from these solar oscillations, would be very subtle compared to other kinds of activity that you would see at the surface. Now, because the surface of the star has convection going on, you see a lot of bubbling and roiling, these kinds of granular cells, as we call them, granulation at the surface, as we call it. And these would be a much more dominant signal that you would actually see at the surface compared to these more subtle and gentle oscillations.
I mean, I think about, say, Cepheid variables, where you've got this star that is changing in size from something that is, relatively compact to something that is engulfing the orbit of Mars within a couple of days and then going back down again. And it's a very, like, you would absolutely just watch this star just disappear under your feet if you were standing on the surface. So it's nothing like that on any kind of scale.
No. Cepheid variables are much larger in amplitudes when we talk about their pulsations.
Right. Okay. And so then, it is a fairly subtle change that's happening on the surface of the sun. So how do astronomers measure this and tease away those other things that you talked about, these prominences and flares and, all of this activity that's going on the surface of the sun?
Well, for the sun in particular, the time scale for which these variations happen are typically much faster compared to all the other kinds of activities that we talked about. For instance, you might get contributions from star spots, for instance, and that would come at a time scale that is comparable with the rotation rate of the sun, which will be typically close to a month or so, right? So the pulsations that we talk about in the sun are at a 5-minute time scale. So these are much, much faster compared to some of these slower, much larger contributions. So that helps a lot. And actually, for us to actually disentangle these variations, we just have to look at the part of the time series or the frequency spectrum that actually more or less corresponds to that area that we actually care about when we talk about pulsations.
But are you like doing spectroscopy on the sun and then measuring the redshift back and forth in this 5-minute interval? Or like, what are you doing to actually say this part of the sun is oscillating at this rate by this amount?
You're right. You nailed that one. We were actually doing spectroscopy and we're measuring essentially the red shifts or the blue shifts of these spectral lines to measure these variations within the sun.
Okay. And so then what does this tell us about the interior of the sun as well as other sort of features about the sun?
Right. So in terms of the sun, because these oscillations, these are what we call P modes, right? So the P stands for pressure because the restoring force within the convective envelope. The restoring forces for these oscillation modes are from pressure. So these modes are excited within the convective envelope of the star, and then they propagate globally itself. So it tells you a lot about the stellar interior in terms of the composition of the star and the density of the star and so on and so forth. Because you can imagine what's happening here. These are acoustic waves that propagate within the stellar envelope. So how fast these waves actually travel within the envelope tells you a lot about the interior sound speed of the star and correspondingly the density of the star itself. So to first order, these oscillation modes can tell you a lot about the mean stellar density. And on top of that, you have not just one type of pulsation modes. As I've talked about before, that the oscillation modes within the sun and other solar-like stars, these comprise a superposition of different kinds of modes in particular. And different modes can penetrate up to different depths. So they propagate up to different depths within the convective envelope before they eventually reach a turning point, and then they travel back out to the surface. And what this tells you is that if you measure the properties of individual modes, you can learn more about the deep interior of the star as opposed to just learning about a broad stellar quantity like the mean density of the star.
Now, but I mean, like, people are probably very familiar with seismology here on Earth, and it's a very similar process. You get an earthquake, the earthquake causes waves to pass through the Earth. You measure the refraction, the reflection, you measure how those waves change as they move through the Earth, and that allows you to sort of probe the interior of the Earth. The source are the earthquakes. What is the source of the waves, these waves on the sun?
It is convection, energy transport. So when you have convection that's bubbling or roiling around within the envelope of the star, you have these small perturbations to the stellar structure. You have these small density changes, and that will trigger these waves that eventually propagate all the way out to the surface itself. It's the same thing as Cepheid variables. It's some instability in the structure, that typically causes these waves to eventually propagate all the way out.
Huh.
But not the mechanisms are not the same. Sorry, I just talked about Cepheid, but I do have to say that the mechanism between the solar-like star and the Cepheid are very different. But the origin, fundamentally, it's an instability or perturbation in stellar structure.
But I kind of imagine, like, you put water, like a little bit of water on a stove, and you let it boil, and you get these little convection cells that are down in the bottom of your pan, and they're popping up and spraying water up into the air. If that's the sun, as these convection cells are rising through the sun, they're causing waves as they reach the surface and release energy. They're causing waves. And so the measurements that you make of the surface of the sun is sort of the sum of all of this convection that's going on across the entire solar surface.
That's right.
Yes. Yeah. Wow. That's really interesting. Okay. So I guess this is how we know this is how we measure it. We know what's causing it, but what does this tell you about, say, the age of the sun?
Yeah. And I think at this point, it's good to first talk about how we measure ages of stars.
Yeah.
So there is no
in the past, right? Like measuring ages of stars was such a rough thing to do in the past. But yeah, absolutely.
It is still a hard thing to do now. It's arguably it's the most difficult measurement that you can actually do in stellar astrophysics, right? It's something that everyone wants to know about. What is the age of this star, et cetera, et cetera. But it's ultimately a difficult endeavor, and it's not something you can do currently. We can do currently without stellar models. So these would be synthetic models. We basically simulate what a profile of the star would be like. You take your stellar evolution code, something like MESA models for stellar astrophysics in particular, and then you basically simulate the evolution of a star. You simulate the profile, the density profile, or the chemical profile of a star that's evolving along the main sequence, and you observe its time evolution typically. And you do this for a whole bunch of different initial conditions. You vary your mass, you vary your chemical composition, and then you use those as a reference point. Because for every stellar model that you generate, you have also a series of observable properties. You have the temperature of the model, you have, say, its metallicity, and so on and so forth. So you take these output observables that you get from stellar models, and then you compare it to your observations, and you ask, okay, I have measurements of this particular star. It's maybe like 5,000 Kelvin in temperature. It's kind of luminous. Maybe it's like 10 solar luminosities. And then you use that and you compare it to your grid of models. And then you ask, okay, is this a model with this age? Does it have more or less the same observables as what I observe? And that is how we do it, how we attribute an age to an observed star. You use models for comparison. So it's the same thing that we do effectively with astroseismology, except now that we have much more information about the star itself. Because we have the seismic information, you can effectively, for sun-like stars, for stars that pulsate like the sun, or what we call them solar-like oscillators, we can also you can learn about the mean density, the surface gravity, and to some extent for stars lower in the main sequence, you can also learn about what is roughly the central hydrogen abundance remaining within the core itself. And you can use that additional bits of information to constrain your models much more effectively, as opposed to previously when you did not have that information. You just had, say, temperatures or luminosities. So it is the availability of this additional information that seismology can provide that's really what people talk about when we say, we're getting an astroseismic age, for instance.
Right. Well, give me a sense of the error bars pre-astroseismology. If you did as much as you could to understand a star and you had to guess the age of the star, but you couldn't use astroseismology, what is your plus or minus range on a star typically?
So pre-astroseismology, I believe that the best ages that we could have obtained would be if you had, say, an open cluster. If you have an open cluster of stars, these are all assumed to be born at the same time from the same molecular cloud, so it has the same composition. And you take the whole population of stars and you try to fit an isochrone to it, and then because they're all co-eval, you can roughly find an isochrone with a very precise turn-off age. This is when the star exhausts hydrogen and starts to evolve into a red giant. So you can roughly fit that feature very well in isochrones, and you can get, I don't remember the exact for that one. It was probably up the order of 10% or even smaller. You can do that very well. But the problem with the previous approach was that it had to be stars that are co-eval. Like, you can't do this for any arbitrary field star, And so now if you try to do this for, say, random field stars, say a red giant in the field, it's not tied to any known population, you can say that the error bars would be like 40, 50%, just using chemistry or just using the star's chemical abundances and its luminosity, for instance.
Right. Like if I showed you just some random sun-like star, it could be off by 50%. You could say, well, this star might be 2 billion years old and this star might be, 5 billion years old. Like, it's huge, the range. Yeah,
that's right.
And yet if I could sort of slice it open like a watermelon and you could look at the internal structure of it, you could come with a much better estimate. And is that, you mentioned sort of the reserves of hydrogen. Is that sort of what you're looking for, is how much of its interior fuel it's used up in its core?
So that applies mainly to dwarf stars. So stars that are still on the main sequence, like our sun, it's still burning hydrogen. So when the star is still in the main sequence, what happens is that if you can measure what we call the quadruple oscillation modes. So to back things up a bit, when we talk about these pulsation modes for the sun and other sun-like stars, we talk about spherical harmonics. We characterize the geometry according to spherical harmonics. And then you have radial modes, which means that the star just pulsates inwards and outwards, like Cepheids, you typically have radial oscillations. And then you would have these dipole modes, which would correspond to a different kind of geometry of pulsation. So if you think of the star as a sphere, you can have it like being elongated up and so on and so forth like that. And then you also have a quadruple mode of oscillation, which is a bit more convoluted, but it's probably more like almost like a horizontal perturbation at most. But this is something that's well characterized by spherical harmonics. But to put it more concisely, we characterize the oscillation modes in sun-like stars typically through the radial mode, the dipole mode, and the quadruple modes itself. So these correspond to different waves that propagate up to different levels within the interior of the star. And what we normally do in astroseismology is to look at frequency differences between each of these individual oscillation modes. That will tell you things about the sound speed within the interior, or the gradient of the sound speed within the interior of the star as well. So it turns out for dwarf stars that are still burning hydrogen along the main sequence, these frequency differences that we calculate, say between the radial and the quadruple mode, for instance, it gives you a very powerful tool for investigating the gradient of the sound speed within the star. And that this in particular is sensitive to how much hydrogen is still burning within the interior of the star. And so we like to measure the ages of stars on the main sequence as its main sequence lifetime. Also, typically how much hydrogen it has left in its core before it starts to turn off, evolve into a subgiant, and become a red giant itself. And so the whole point of this is to say that if you can measure this particular quantity, this frequency separation that tells you, that is sensitive to how much hydrogen is left in the star along the main sequence, you can determine the ages of dwarf stars fairly accurately.
Right. So if I showed you a star and it was actually the sun, but I didn't tell you, and said, look at this star, look at the harmonic data of this star, how closely could you measure how accurate could you predict the age of this star, of this yellow dwarf star?
I would say fairly precisely if we have other complementary data on it as well.
All the data you want, especially the astroseismology data.
Yeah, I say that we can do a very good job at estimating, because it's a bit of a
within a couple hundred million years, within a couple of billion years. Like I'm trying to, we know it's 4.5 billion years old.
Yeah,
what error bars would you give me?
But I would say up to a few percent for sure.
Wow. Right. So improved from 50% to a couple of percent.
Yeah, but actually, it might be a bit circular now that you think about it. Now that you mentioned, if you want to go back at this and measure the age of the sun using astroseismology, because ultimately all our models right now they typically are calibrated to the sun. So right. we want to have something with sun-like observables that's actually corresponding to the age of the sun within about 4 gigayears or so, right? So ultimately, I guess the question here would be for other dwarf stars that we see. We have models that are calibrated to the sun. Given that these are solar calibrated models, what is the precision if we were to try to estimate the ages of other sun-like stars?
Yeah. I mean, obviously there are other models. I mean, you mentioned the clusters. I mean, the clusters give you the best comparison, and then there's going to be models from those cluster stars, and then you can sort of compare and contrast those versus the sun. And I'm sure it's this ever evolving field as people learn more, new simulations, more models, get better and better accuracy as you go. Obviously, ideally, you would collect meteorites from other star systems with stars, yes. and then
that would be amazing if we could do that.
Yeah. And the next Oumuamua would have passed through. If we know what star system it came from, that would be very helpful.
Well, we can hope for something from Alpha Centauri potentially.
Yeah, that'd be great. Yeah, someone finds a meteorite on the surface of the Earth and it turns out it came from Alpha Centauri. That would be phenomenal.
No.
Okay, so let's talk about now the technique. So now we've got this technique, this astroseismology that's been pioneered, and a telescope we've heard that's doing a lot of really interesting work is the TESS mission, which is searching for exoplanets. So how is it helping in seismology work?
Well, the TESS mission is effectively looking across the entire sky. It's performing photometry, so it's staring at millions or hundreds of millions of stars, and it's basically just giving us continuous, uninterrupted light curves And what we call light curves here are simply just time-resolved measurements of the intensity of light that's coming from stars itself. Okay, so perhaps at this point it's good to contrast this or to back things up a bit, because we first talked about helioseismology and collecting spectra and measuring red shifts and blue shifts. So that's one way. I would say perhaps the traditional way. I don't know how we've done measurements, or we discovered oscillations in the sun. It's basically through velocity measurements. But there's a second way of how we could actually measure these oscillations, which is through intensity measurements. So while one approach, the first approach, uses velocity, the redshift and blue shift, this one here, we're actually looking at how the intensity of the light changes as a function of time. Because as the star expands and contracts, right, you think of it as this giant balosphere expanding and contracting. You effectively have a change in the temperature of the star as it expands, right? When it expands, it cools down a bit, and when it contracts, it heats up a bit as well. And that will change the total amount of light that's actually being emitted at any given point. So if you have a photometer that's staring at a star, just collecting photons from it over time, you would see the same sort of variation that you actually would expect to see based off the velocity, from variations in velocity. There is some phase difference between them, but that's a bit going into the technical side. But back to the point, this is the second approach that we've been doing to measure oscillations. And we've done this in the past with space missions, from the European Corot mission, as well as the Kepler mission from NASA, which is also another exoplanet hunting mission. Now, why a space mission? Why we can't actually do this from the ground? Well, it's because of the atmosphere. The atmosphere makes it incredibly difficult to collect extremely precise measurements. Because early on in this interview, we did mention about how subtle these variations are. You need to have extremely precise measurements to actually capture these variations in stars like our sun. For Cepheids, probably it's fine. It's okay. You can probably just take these ground-based surveys and you can observe these gigantic variations in light that's coming from there. But for the sun and other sun-like stars, you have to really rely on precision photometry. So with space missions, it began with Corot. We first started to observe these pulsations mainly in more evolved stars, because there's a trend that goes in such a way that if you have a star that's more evolved, like a red giant, if it's bigger, it tends to have pulsations that are more violent, so larger in amplitude. So because these space missions gave us continuous, uninterrupted photometry, we could really resolve these pulsations really nicely. But the field of astroseismology in general really was revolutionized from the Kepler mission, because it was such an amazing, precise photometer. And it stared at only one patch of the sky. It looked at roughly 200,000 stars, but its precision was exquisite. It observed faint stars, but it gave us 4 years of uninterrupted observations. And because we deal a lot with frequency information that's coming from these stars, we want data that's homogeneous and as uninterrupted as possible. And the Kepler mission truly delivered on that front. It gave us exquisite data, extremely precise in terms of its frequency resolution, and it opened up so much for us in our understanding of solar-like oscillators itself. We've discovered so much information within, say, the mechanisms of dwarf stars, of the evolution of angular momentum in dwarf stars, of magnetism in giant stars, for instance, as well. And it is a gift that keeps on giving, even till today. The Kepler mission has been retired for many years now. Many of us in the community are still digging into the data, still finding new bits of information to tease out in itself.
Is it like like with Kepler, they lost the reaction wheels and had to change the nature of the mission? So you've got like a year's worth of the pre-damage and then the post, when they did the sort of follow-on methodology of using light pressure from the sun to balance the telescope. Is there a difference in that, in those data? Like, do you prefer the pre or the post?
Well, definitely the pre. So in this case, I assume you mean that before the reaction wheel got busted, right?
Yeah, yeah,
Oh,
yeah,
absolutely. I think it was during the prime mission. That's when we got the best data, right? Because during the second life mission, or K2 as we call it, you had all these
yeah.
other systematics in your data to consider. For instance, there was this whole thruster firing that had to occur every, was it day or two? But you every very regularly you had to reorient, the telescope itself, and that introduced a lot of artifacts and systematics into the data collection process. That was quite tough to handle, but people still managed.
Yeah. Yeah. It makes me so sad that, I mean, that was the spacecraft that would have found us another Earth. It was, and then it wasn't able to complete that mission. And so here we are, as you say, close to 20 years since that mission launched. And yet still we don't have that answer. And we're going to have to wait for some future mission, probably Plato, to get us that answer. So
It's somewhere along the horizon. So I think
yeah.
perhaps we don't have to wait that long.
So what is what is the forefront? What is the sort of leading edge of this technique now of using astroseismology to understand the ages of stars and sort of what's going on their surface? I sort of think about, say, exoplanetary search, people who are searching using the radial velocity method. The state of the art is 50 centimeters per second, but they're trying to bring it down to the point that they can actually start to detect the influence of, say, an Earth-sized world orbiting around a sun-like star, and that's going to require 10. So,
Right.
So where are you at now, and sort of the kinds of objects that you can observe, you can get really useful information on, and what's the stuff that's kind of a dream right now with the current suite of instruments?
Well, in terms of just precision, stellar astrophysics of, say, cool stars. By cool, I mean like dwarf stars and red giants. I would say that Kepler was and is still the state of the art in just delivering the best data that we can. In terms of large scale studies involving astroseismology, we would have to say that it is TESS. I've talked a lot about Kepler in that past block that I was talking about, but TESS really shines in being an all sky mission, and it's enabling a lot of different kinds of science that we haven't really been able to do with the Kepler mission. So one example here is the astroseismology of, say, more massive stars. Because the Kepler mission had limited bandwidth, it could not collect and downlink data of any type of star. It only had to go through a very careful target selection process, and this meant ignoring a lot of very other interesting stars that would have been very interesting as well. And these include like the OB type stars, the A type stars. These are hotter, more massive. They're interesting in their own regard, but probably just not They're not that interesting of a planet host. That's why they weren't selected for the prime mission. But TESS doesn't have that distinction, right? It's just looking across the entire sky, and because of that, it's really right now it's the mission that's giving these folks who study these more massive stars the state of the art information in terms of what you can actually reveal about the interiors of these more massive stars itself. So that's basically trading off one small patch of sky versus observing everything across the entire sky itself.
And so back to that example that I gave you earlier, if I showed you this star, we're going to call it the sun, and I asked you to sort of guess the age of that thing. What is an object, like a smaller object, a dwarf, that I could provide you, and you would just go, I've got nothing? Like, where are we at now where you just, like, if I showed you a K dwarf, would you be able to tell me the age of it? If I showed you an M dwarf, would you be able to tell me the age of it? At what point does the sort of the observations outstrip our ability to make them?
Well, we have model predictions of what these very low mass stars should produce in terms of, say, their pulsations. It's really the observations that are currently that we are currently lacking in terms of not being able to observe something as small as like a really, really cool K dwarf, for instance. So I'm still ready to be surprised. There could be an object out there that's just completely baffling, that doesn't conform to what we understand about stellar evolution. And there definitely will be things that pop out every now and then in the data that just constantly demands our attention, that revisit some aspects of our understanding of stellar evolution.
But I mean, there's this. I mean, there's a real controversy right now about the habitability of planets around M dwarfs, and the assumption is that in that first billion years or so, they're just getting hammered by solar flares and activity from the star, and yet if you could sort of reach a little bit after that, then maybe things can settle down. But if you could, with precision, know the age of a star, you could know whether or not, like, really when that activity is settling down, how long have those planets been there for. I mean, there's a lot of really useful information, and the cave dwarfs are even more interesting. I mean, they're less mass than the sun. They're probably going to live for whatever 70 billion years, and they're not as awful in the early phase as the M dwarfs are. So there's a lot of really interesting science questions that I'm sure you must have. So let's get to the good part now, which is, what's it going to take? So right now, I mean, you're using archival data from Kepler. You're using tests to do a job that it wasn't primarily intended, although I'm sure that was built into the requirements at the same time. What's it going to take? What would be your dream instrument to be able to actually perform the level of astroseismology that would get you all your answers?
Yeah, it's a great question, because there are recent developments that's really starting to bridge this gap between what we have done and what we are able to do in the future. So there was a paper that I recently published that talked about using this new instrument up in Hawaii on Mauna Kea Observatory. It's called the Keck Planet Finder, and as the name implies, it's a radial velocity tool. It's an extreme precision radial velocity tool that's meant to, by design, it's meant to detect these really small planets, perhaps like an Earth-like planet around these nearby stars itself. So it has an exquisite precision, and in principle, it's able to reach a precision level that no other instrument has in the past in terms of radial velocities. But as we've talked about as well previously, we also know that the pulsations of dwarf stars, they tend to be much more low in amplitude. They tend to be much more gentle as you move to smaller, low mass stars like K dwarfs. And so because of that, we could use this instrument, this Keck Planet Finder, and try to measure oscillations, velocity variations at the surface of K dwarfs. And this is exactly what we've done in this paper that I published. We did this for this nearby star called Sigma Draconis, or Alsace, which is a star that's about 6 parsecs away. So it's very close, one of the nearest neighbors to the sun itself. And it's one of the favorites among the folks who do observing, because it's a naked eye star. It's really bright. It's fourth magnitude. And there's tons of archival data in the past. Just people have been staring at it with radial velocity measurements for a long, long time. But in any case, because this instrument that we have now is so sensitive to variations in radial velocity, you could effectively just point the instrument and collect data from this star, Sigma Draconis, over the span of a night, and look at the variations in velocity. And that is exactly what we did. We just collected data across 7 hours, just one night of observations. And lo and behold, the oscillations were there, just right there in the data itself. It sticks out. It's so obvious that there's pulsations at roughly a 5-minute time scale. And these show these very similar characteristics to the solar oscillation spectrum itself. It was a beautiful data set that we have collected with just one night of.
So it turns out that other stars do what the sun does. You've now confirmed. Can confirm.
Well, we've known this for a long time, right? As long as it's relatively low mass, it has a convective envelope. Anything that has a convective envelope will have these stochastically excited pulsations, which are similar to that of the sun.
Now, this was, as you said, it's a naked eye star. It's one of the most sophisticated instruments on Earth, and it was able to give you this really pristine data on this one star. But how do we survey this? How do we Gaia this? How do we get accurate, data on 1 million stars simultaneously? that would be useful, right? If I could give you a catalog that give you all the astroseismology data on a million stars, if you could do queries on it like Gaia,
Yeah.
would that be helpful?
So I think you've hit the nail on the head there about why also photometry using space missions is much more catalogable, if that's even a word, as you try to phrase it, compared to these radial velocity measurements. Because these radial velocity measurements are done from the ground, and they often have to focus on a single target throughout the night. It's very resource intensive. Whereas if you have a space photometer, you just have this camera that's out there in space. It's just observing millions of stars simultaneously. So you instantly have this whole bulk volume of data, as opposed to radial velocity measurements that we've done that's much more boutique. It's very focused on single target at a time. But maybe to extend this into the future, if we could have something that could do these RV measurements simultaneously, it would be excellent. It would be amazing for the field, right? Because effectively right now we have quantity versus quality. Because right now with the extreme precision radial velocity instrument, we are definitely pushing the boundaries of which stars we can actually detect these pulsations and, in extension, determine their age. Because I have to say this, what we show in the paper about Sigma Draconis is that you can actually see the same pulsations within the photometry from TESS. However, it is at the very limit of detectability. It's really difficult to see because, well, pulsations are really small, and of course TESS has a limit in terms of the sensitivity of the variations that it can pick up. These variations that we see in TESS corresponding to the oscillations are at an amplitude of roughly only 1 part per million. So you can imagine that is such a small fractional variation in the star that we are measuring in TESS. And so that's really hard to spot in the TESS data. But if you just look at the radial velocity data, it sticks out like a sore thumb. There's no way you can miss it in its entirety.
But I mean, up until this point, the best photometry, the best astroseismology observations have been done using planet hunting surveys. If you were to design a mission, will it always be the case? Will you have to pull your data from existing planetary surveys because essentially the science case is almost identical, that a better planet hunter is going to provide a better astroseismology? Or is there a place where you could diverge? You could imagine designing an instrument or a mission that is fantastic at doing astroseismology, but actually isn't that useful for planet hunting, or will they always be the same tool? And one is, one is the charismatic megafauna, the planet hunter, the thing that finds us Earth 2.0, the one that tells us whether or not we're alone in the universe. And then there's the other instrument that is, trying to measure the
that's a really great
pulsations on the star.
question. It's because we have such a huge synergy with the exoplanet community in terms of just wanting precise light curves in itself, just wanting something that can really pick out variations that are extremely tiny. But I suppose where we would differ mainly would be in terms of target selection, right? Because the exoplanet people would certainly want to target planet hosts that host planets that are interesting to their science case, which stars are more likely to harbor rocky planets, for instance, or gas giants, and so on and so forth. Whereas the stellar community would be, of course, tend to focus more on just it will be guided more by the stellar astrophysics itself. Where are we more likely to find populations of stars that have very interesting characteristics or weird things going on within the interior that just typical boring sun-like stars don't have?
But I wonder, is it about the duration that you're pointing? Is it the wavelengths that you're looking at? Is there anything that differs between the needs of the exoplanet community and the astroseismology community? Or is it the exact same telescope, is the exact same mission that you will always be sort of working together?
Well, in terms of duration, for instance, we care in the astroseismic community, we care a lot about just how long you want your observations to be. And to some extent, you can argue that the exoplanet community also um, cares about the duration of this, because the more transits you get, for instance, you get a higher signal to noise, and can potentially also detect longer period planets. But for us in the astroseismic community, it is much more about the resolution of the frequency, the individual frequencies that you can actually collect as well. So
yeah.
that's one particular requirement.
I wonder if I'm like asking my question properly. Like I just sort of imagine if NASA came to you and said, we just want to build an astroseismology mission. We don't care about a planet hunter. And this may be rendered unusable for people who have any interest in using this instrument to look for planets. Would there be a mission, or is it it's exactly the same tool that what the planet hunters require?
This is an interesting question, right? Because some of my European colleagues, have thought about this and been trying to pitch for a mission in the distant future that actually does this kind of thing, right? You just have a mission that's dedicated to astroseismology. You just take this precise photometer and you just stare at this stellar population, something that's very interesting from a stellar astrophysics perspective. So this would be typically something like an old globular cluster where we're really trying to disentangle stellar evolution. And you can stare at something like 47 Tuc or like a dwarf galaxy, for instance, and you just want to disentangle and reveal all the different kinds of information that's within different parts of the stellar population itself. So there, we don't really care about the planets. We care more just about the variation seen across all stages of stellar evolution. Now, in terms of the specifics for the instrumentation, I'm not sure that there would be much of a difference, because we ultimately still want very precise light curves. But in terms of wavelength coverage as well, not too familiar with what the planet people would like across different wavelengths. But I can say, in terms of the astroseismology, that we would love to have the different wavelength coverage. Say if we have something in the red and something in the blue separately, as opposed to what we've had now, which is basically only information that collected in the optical. So we only had broadband photometry for everything so far. And we know theoretically that there should be some differences between the, say, oscillation amplitudes that we measure in the red versus in the blue. And this will allow us to do some really, really interesting physics with these oscillation modes that we can actually see as well. And we haven't had the ability to do that yet. And that would be really cool to have in the future.
Yeah, I mean, like the targets for sure. I could imagine a mission that's just designed to look at one globular cluster or one dwarf galaxy, as you say. But of course, you can imagine you're staring at 47 Tuc for 3 years continuously, doing photometry on every star in this cluster, and the exoplanetary folks would be saying, "Can we look at that data?" Right? Because I'm sure there'd be some interesting planet data in there as well. So it wouldn't be their primary target that they would want to look at. They're not the best places to look for planets. You wouldn't want to necessarily live inside a globular cluster, but still there would be really useful, interesting variations. I mean, if they detected planets in globular clusters, that would be a pretty fascinating science discovery as well. So no, I think you folks are inextricably tied together forever.
Our fates are intertwined for sure.
Yeah, totally. Yeah, I can't imagine anyone going like, we're gonna build this mission and it's gonna have a photometry component, and it's gonna have a planetary component. I can't imagine anybody ever coming up with anything apart from that, because, as I said, the planet hunters, that's the thing that gets the news, the buzz. I do a lot more stories on exoplanet hunting than I do on astroseismology. So, Marc, what are you obsessed with right now?
Currently, what I'm obsessed about is truly diving into the test mission, right? Because it is a treasure trove of so many interesting phenomena. We have now access to information, seismic information across the entire sky. And this is revealing some really, really interesting and weird objects. For instance, like you have planets that perhaps shouldn't really exist around systems, like planets existing around giant stars. You have really old stars that have come wandering into our solar neighborhood, and now we're trying to investigate, how these stars came about. What we call this is galactic archaeology, trying to understand the formation history of our galaxy in particular. And so, what's been keeping me hard at work right now is just understanding where all these different pieces come together. Playing, I like to liken this to playing a stellar detective, because what happens now is that you find a weird object, it's really weird, it shows some interesting seismic information, and then now you go back and look at all the historical archival data, because TESS looks at mainly nearby bright stars, and these stars have had perhaps decades of investigations being done by different groups. So now you can go back and see all the different information that people have collected from it in the past. Is it historically known as a weird object? If it is, and now you have seismic information that makes it doubly interesting in particular, right? So it's been a lot of fun, I have to say.
Yeah, like anomaly hunting in test data.
Exactly, and it's giving us the ability to learn about so much more than we've had in the past.
But when I think about the observations that you made with Keck, compared, like TESS is just giving you the faintest hint that something weird is going on with this star, compared to the really precise data that you're getting from something like Keck. So what's the weirdest thing that you've seen? What's something that you still are pretty puzzled and confused over? What's an anomaly in the data?
So in last year, I put out a paper that talked about this particular giant star. It's called 8 Ursa Minor, and it is a star that, through seismic means, we have determined that it should have once expanded to a really large size before reaching the tip of the red giant branch, where it becomes like maybe 100 solar radius in size, gigantic. Before now, it's in the quiescent core helium burning phase, so it should be a much smaller star as it is right now. So that would be fine and dandy if it weren't for the fact that we seem to have detected the ongoing presence of a close-in planet around this particular red giant star. This is a planet that, by all means, should have been engulfed in the past, but it still remains today, despite the fact that stellar evolution has dictated that this star has blown up in the past and engulfed this. This star had blown up and engulfed the planet.
I think I remember this story. Yeah. So this planet spent some time inside the envelope of the star and survived.
We don't think it had actually been engulfed at some point, because all the simulations that we've ran indicated that, if at some point the planet was engulfed, it just should have just spiraled into it. There was no way it would have survived engulfment. So how did this star actually get from the giant branch phase to the core helium burning phase without actually swallowing up this planet? It's kind of an open mystery at this point. We have some theory about how this might have happened based on just a simulation, but further follow-up is clearly needed to confirm this.
Yeah, that's really cool. One last question for you. When is Betelgeuse going to explode?
Oh, wow. That's a really tough question. Betelgeuse is such a hot topic right now.
I know.
I would love to say, within our lifetimes, but I would have to say in 100 mega years. Ooh, that might be a hot take.
100 mega years, 100 million years?
Perhaps even shorter.
Yeah.
Few million years, maybe.
Yeah. So we might need a robot body then.
Don't quote me on that. I'm just spitballing a number right now, but I know
okay, all right.
People would love to know that Betelgeuse is going to explode in like a decade or so, light up the sky.
Yeah, that would be great. It would be a game changer if we actually saw it go off. Well, Marc, that was super fun. Thank you so much for your time, and thank you for providing this in-depth explainer on this really interesting topic. I hope you enjoyed this interview with Dr. Marc Hon, and this filled in a lot of the missing pieces in your understanding of astroseismology. Now, I'm going to give you some of my thoughts and feedback, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Barry Lake Roofing, David Gildenan, David Matz, Dennis Alberti, Dustin Cable, Jeremy Maddern, Jim Burke, Jordan Young, Josh Schultz, Paul Rohrbach, Spiderswap.io, Stephen Krasaki, Stephen Fowler-Munley, and Vlad Shiplin, who support us at the Master of the Universe level, and all our other supporters on Patreon. So the interview that I was talking about was with Dr. Gerard Van Bell, and it's sort of the previous interview on the channel, and we'll put a link in the show notes. You can go and listen to that interview if you want. And in that interview, we sort of talked about how there's been this revolution in astroseismology. And it really is just kind of amazing what astronomers are able to do when they are able to measure these subtle variations on the surface of a star to determine the interior composition and the age of the star and a lot of other really useful information. But as you can see, this is one of those fields that we're just in the infancy. Really, this level of clarity has only come from Kepler, which died too soon, and then the work with TESS, which is an incredible mission, but not sort of at the same scale and budget and optics that Kepler had. And so really, all this incredible headway has been made without a real flagship mission being able to do the kind of work that could produce that enormous survey, the Gaia for astroseismology. And yet we've got the upcoming Plato mission that's going to be doing a lot of this kind of work, and other telescopes that are still being dreamed of by astronomers. So if there's one field that we've been able to watch just go from its infancy to its young age now, and hopefully we'll move on to its maturity and give us a lot of really incredible scientific discoveries, it's astroseismology. All right, hope you enjoyed this interview. Thank you, everybody who asked for this interview. I'm happy to provide, and we'll see you next time.